Morning. We now start the webinar, live streaming of the webinar, discussions regarding the operations research course. So we will take the questions as they arrive. I think there are an initial set of questions which I will answer, and then as these questions come, we will try to answer them.
Tabular simplex algorithm is very difficult to understand. Please explain in a simple way.
Okay, let me take that question first. I think when I started explaining the simplex algorithm, we first do the graphical method and then we do the algebraic method. And then we do something called an algebraic form of simplex, where if you see carefully, I would have written the basic variables as an equation where the non-basic variables come on the right-hand side. And then I would have related it to the objective function and said that initially the objective function is at 0, and if you want to increase, you can increase any of the non-basic variables. And then we try to see the extent to which it can be increased without affecting the feasibility. And then we go through that process in an algebraic form. And at that point, I would have said this is the algebraic form of simplex. And we try to put that in the form of a table. And then the tabular form or the form of the table is only a convenient representation where you don't have to write the equations every time. And depending on the position in which you write a number, you can see the corresponding variable on top of the table. And therefore, every row of the table in any iteration can be easily read as an equation. I think the only place where you will be able to relate number by number. If you take a typical problem, you will be able to relate number by number what you see as Cj minus Zj and what I would have explained in the algebraic form of simplex. So I don't see a problem in understanding that. I'm also not sure if you are, I don't know who has asked this question. We have specific videos for this MOOC's course. We also have some OR videos of mine which are available in NPTEL. There are 22 videos in the fundamentals of operations research. If you happen to view them, then I would have explained the thing in a slightly different or in a slightly different manner, or I would have spent a little more time explaining it in those because those are all almost 1 hour videos. So, in practice, or when you actually try to solve larger sized problems, we don't use the tabular method. So tabular method is only for hand computation. The only place where you may not be able to relate it would be what is the Cj minus Zj, other than saying that it is the rate at which the objective function increases. Is there a mathematical approach to Cj minus Zj? That can happen if you have a strong maths background or maths inclination. But one can do all that. I have deliberately reduced the proof and derivation part of the course, and I have tried to position this course somewhere between computation, where the emphasis is more on computation and understanding what happens in the simplex algorithm, and perhaps with a mind where how these things can be applied. So I have tried to do those two things. So detailed description of the simplex table, I think you should try and see the other videos of mine, which are there, called Fundamentals of Operations Research under NPTEL. And of course, there are a lot of material which are available, which you can read and understand the simplex table.
Operations research application in supply chain management.
Yeah, I think there is a question called operations research application in supply chain management. Once again, I am not sure about the background of the person who is asking the question. So therefore, I'll try to give a very general answer. If I have a chance to know the background, I can even try and give a more specific answer that would suit the background. Now, supply chain management is, you can think of it as an application area. And operations research, you can think of it as a tools, a set of tools, which okay, so you can think of operations research as a set of tools which help us in solving the application problems in supply chain. Assuming that you have some background in supply chain, the important decision making or decisions in supply chain are classified into four, which are called location decisions, production decisions, transportation or distribution decisions, and inventory decisions. If you see carefully, all the four areas, there's enormous opportunity to apply the tools of operations research. Location decisions lead to a class of study called location and layout problems, which is a separate area by itself, but you can use tools of operations research. The problem, general location problem or layout problem becomes a quadratic programming problem to begin with. We haven't done quadratic programming in this course. Layout problems at times are modeled using continuous functions, and you can differentiate and get the answer. But if you are very specific about the tools that you learn in this course, like linear programming and so on, they help us in solving some production problems. In fact, the first example itself is a product mix problem, which is like how much to produce. And the same thing can be used in the context of a supply chain. The production planning problem that we have seen can be used in supply chain. Now, regarding transportation decisions, I'm not going to say that the entire transportation decision reduces to the transportation problem that we see, but the transportation problem that we have seen in this course is actually a starting point which starts the whole thing by saying, here I have certain things and how do I distribute them to different places. Additional topics which are not done in this course include traveling salesman problem, vehicle routing problems, which are used even more extensively in the area of supply chain. Supply chain also integrates, for example, it integrates the total cost function in a supply chain could be a sum of all these costs. At a beginner level, we see all these problems as separate problems. You also need to do an advanced OR course to understand some more tools, because normally we do integer programming in the advanced OR course, and most of these problems become integer programming problems, particularly the location problems, layout problems, and so on. So there is enormous opportunity to do, but we haven't done that in this course, because this course primarily introduces you to the tools. Once again, it's a first level course, so the real applications will start after you do one more course and try to specialize in that area.
How exactly does any real-life problem bifurcate away from the problem formulation we try to solve in this particular course in the viewpoint of the prior assumptions?
So what happens is the simple problems that we have formulated in this course have some very, very well-defined assumptions. Whereas real-life problems, you may not have those kind of very well-defined assumptions. So to that extent, they will be different. The typical textbook problems are problems that we have looked at. They're clearly told. The problem statement will very clearly tell you, and if you read the problem statement one more time, let's say, read it 2 or 3 times, you will quickly know what is the decision variable, what are the constraints, and what is the objective. When you start modeling a real-life problem, first of all, the scope of the problem has to be defined, which means the assumptions also have to be defined. So what are the things we are going to include, what are the things we are not going to include. So all these have to be defined. Second is that the time it takes to formulate itself is much more than the time it would take to formulate the kind of exercise problems that we do. I'm not saying that, or I'm saying that real life problems can be modeled using what you have learned in this course. But then it is not done normally by a single person. Initially, the scope has to be defined. The parameters that we are going to include have to be defined. What we are going to consider, what we are not going to consider should be defined. And some places the assumptions will be a little, different people may view it differently. So in reality, real life problems, formulation would involve multiple people. It would also involve a group of people. It would involve different stakeholders to the problem. At times, different stakeholders might have different specific objectives or local objectives or immediate objectives, while the objectives would be in tune with that of the organization, but still they might have some immediate objectives which can conflict. So all these have to be resolved. So sometimes they become multiple objective problems. We haven't looked at that in this course. So they all have to be resolved. So the answer is this is a starting point, and this doesn't give us the immediate ability or immediate, the entire skill set to do that. But as we start doing this over a period of time, we learn how to model real life problems.
Any thumb rules to choose which solution is better than others?
Difficult to understand the question. I don't know the context in which the question is asked, because particularly in OR problems and the way we have seen, given a problem, there's only one solution. So I can't understand what you mean by saying which solution to choose. Unless you are looking at, say, for example, heuristics or thumb rule based solutions to problems, which is a separate field by itself, and therefore it's not easy to give a very general answer to that question. I think I'm going to stop here and not proceed further in that question unless I know the context in which it is asked. What is the application space? What are we trying to understand by saying multiple solutions or different solutions, and so on.
In alternate optimum solution, if every point on the line is optimal, then how does it affect the statement that corner point has more effect than in-between boundary points?
I'm not sure about that sentence, the second sentence. Can you read that again? How does it affect
the statement that the corner point has more effect than in-between boundary points?
Okay. I think, let me try to understand what is told in that sentence. See, when we do the graphical method, I would have drawn or shown a feasible region. And I would have first said that you take a point inside the region. And then for that point, for every point inside the region, there is a boundary point which will have a better objective function, a maximum or minimum. It would have a better objective function than an internal point. And then I would have taken the discussion to saying that it is now enough to look only at boundary points. After that, I would have argued, saying that if I take two boundary points, depending on the objective function, and if you evaluate two boundary points, I would have said one of them would have a slightly higher, or assuming it's maximization, one of them would have a higher objective function value, and therefore it would be better to move in the direction in which the objective function value is getting better till we reach a corner point. I would have said that. So that must have given an impression to write the sentence. And what is that sentence? One more time. More effect than corner point has more effect than a boundary point. So that sentence is applicable to the non-alternate optima case. When I said that if you take two boundary points, one boundary point would have a better value of the objective, assume maximization. One boundary point would have a higher value of the objective function than the other. Statement is made under the case of non-alternate optimum. But when I made that comment, we were too early into the course, and I had not even defined optimum for me to define alternate optimum at that point. Therefore, I would have said that. Now, that statement is not entirely true in the case of alternate optimum, because in the case of alternate optimum, if you take those two boundary points, and if the objective function line is parallel to that constraint in which you have taken both the boundary points, then both will be equal and one will not be better than the other. So if you are asking me specifically to react to that comment in the context of alternate optimum, my answer is that comment was made when we had not defined alternate optimum, or that comment is valid in the case of non-alternate optimum. In the case of alternate optimum, what will happen is both the values will be equal. And therefore, you can move anywhere, either up or down, assuming it's a two variable and line, and under all that assumption, you can actually move in either direction of that constraint, because all of them have equal values, till you touch the two end corner points, under the assumption that we are solving a two variable graphical and so on. So every point in that line has the same value of the objective. The only clarification that you need is, in the non-alternate optimum case, we say that counterpoint solution is optimum. Or if the optimum exists to a linear programming problem, it is a counterpoint solution. Simplex as a tool or as an algorithm evaluates only counterpoints, and therefore it gives one of the counterpoints. And then, assuming once again in the example of a 2 by 2 and graph and all that, Simplex will take you to the next counterpoint. Simplex does not have the ability to tell you that if these two counterpoint solutions are optimum, every point that is in the line joining those two, which is that boundary line, is optimum. It tells you indirectly by jumping from one counterpoint to the other. But that led people to redefine optimum solution. So only in the case of alternate optimum, the optimum solution is defined as any feasible solution that has the same value of a counterpoint optimum solution is optimum. So that is the answer.
Will cycling an alternate optimum solution have any resemblance as they form infinite loop over and over between two particular switching points?
I will try to answer that question, but let me say that that's not really entirely part of this introduction course. Because cycling and alternate optima are two different things. If you see cycling very carefully, cycling is something specific to the simplex algorithm. Alternate optimum is specific to the problem. So to that extent, they are different. Cycling is in some ways, before the anti-cycling rules were given, there are two rules, the lexicographic rule and the Bland's rule. Before they were given, cycling was a case when, for a particular choice of entering and leaving variable, simplex did not terminate at the optimum. It got into a situation where a previous basis was repeating after a certain number of iterations. The optimality condition was not satisfied. In all these iterations, there was always a positive Cj minus Zj which could enter. But the limit was 0, and therefore there was no increase in the objective function. Alternate optimum is a case where the optimality condition is satisfied. For that basis, you have all Cj minus Zj less than or equal to 0. Therefore, they are two different. Even if you look at it from the way simplex solves linear programming problems, these two are two different things. The alternate optimum case, the termination condition is satisfied. the cycling case, the Cj minus Zj condition, there is always a variable that has a strictly positive Cj minus Zj and can enter the solution. So they are two different things.
What is the physical significance of unboundedness in real-life problems? Does it have no solution or infinite solutions?
I'll try to answer this question to the best of my ability. What happens is when, I'm not sure whether I made those comments in the video, but let me again tell this. I always say that when you solve a problem, we later ask whether the problem was taken from a practical application or whether it was taken from a book or whether it was created by somebody. But if you solve a linear programming problem and you get unbounded solution or infeasible solution, we have to ask ourselves two questions. Unbounded, what you have to ask is, check whether you have put the correct sign of the constraint. For example, somewhere if there is a plus 3x1, by mistake have you typed a minus 3x1. And when the problem is infeasible, we are normally expected to check whether you put the constraint inequality in the opposite direction. So these two tips are normally given when you say that I have looked at a real life problem, then I have modeled something out of a real life problem, and then I try to solve it. I'm getting unbounded or infeasible. If you say that, assuming that the real life problem has given you a very small linear programming, and if you come and say that it is showing unbounded or infeasible, these are the two checklists that you have to go back and check, first of all, before you accept the solution, which essentially means, have I made a mistake in the formulation in the first place? Either my own understanding of the constraints, or it could be even simple typos like, have I typed a minus instead of a plus? Have I typed a less than equal to instead of a greater than or equal to? But if you are solving a problem from a textbook, which essentially tries to check whether you have understood unboundedness or whether you have understood whether how Simplex detects unboundedness and all that, those little checklist is not applicable there. The reason those two checklists are applicable is because when you try to model a real life situation, something is actually happening in reality. And you are trying to model it to make it slightly better. Can I get a solution which is slightly better than the solution that is presently being implemented or which is presently happening? Therefore, when you model a real life situation that is actually happening, your model should not result in an unbounded or infeasible solution. Unless you have added some other constraint that somebody feels should be added, and that constraint could have given infeasibility. So that's my answer. So when you are actually trying to model something that is happening, your model, when solved, should not result in unboundedness or infeasibility. Particularly if you are looking at a real life. And if it results in unboundedness or infeasibility, the only answer given is go back and check your formulation again, go back and take every one of those constraints again, then go back and check what parameter values you have given, and so on.
Question. We have a follow-up course on multiple objective problems, or it can be learned elsewhere.
Well, the answer is it can be learned. Where is something that you decide. The person who has asked the question or the person who wants to learn decides. If you ask me, am I going to do that multiple objective course at the moment? The answer is I'm not, because I have a very small component of multi-objective decision making, goal programming and so on in the advanced OR course. Even when I teach advanced OR here, I spend hardly about 2 to 3 classes just telling them what is goal programming as a way to solve multi-objective problems and so on. But if the person who has asked this question wants to learn multiple objective optimization thoroughly, then you have to first do at least 1 or 2 courses in OR, which means you have to do a first level course. You have to definitely do a second level course. You have to learn integer programming much more thoroughly. And after that comes advanced courses on multi-objective optimization and so on. At the moment, I don't see that because we also, at times it's good to offer a very advanced course where only about 100 people can take. But if I align myself with the larger purpose of NPTEL, where you want more people also to go through these courses, and this provides an opportunity to enhance some basic knowledge, then I don't see myself doing that in the near future, unless another esteemed colleague can definitely come up and do a course on multi-objective optimization.
How to extend the problem of simplex once it is optimized by replacing non-basic variable values by some negative value?
I don't understand the question at all. So if somebody who has asked that question can type something, is there a chat where they can? So please, if you can type that question and you want to tell us something more. I think we are still going to be here for about half an hour, assuming that people will be here joining us. So I think when I have much more clarity on that question, I will answer that. At the moment, I am unable to understand that question. Therefore, I am skipping.
One of our teachers have told that in case of non-linear optimization, there cannot be multiple solutions. Can you clear this for us?
It's extremely hard to react or comment on something that has been told in a class by another colleague and so on. It's not fair also because one has to understand the context in which that observation would have been made. However, let me try to add a couple of comments. I'm not going to pass a definite yes or no on that statement. In linear programming, you get one unique optimum solution to the problem if a solution exists and if no alternate optimum exists. If I also read that sentence very carefully, can you read that sentence again?
In case of non-linear optimization, there cannot be multiple solutions. Can you just clear?
Okay, the sentence says there cannot be multiple solutions. The sentence doesn't say there cannot be multiple optimal solutions. It doesn't say that. So obviously the problem has multiple solutions. When I assume that a solution means a feasible solution. I mean, if you take the simplest problem of, let's say, minimize x square. Minimize x square, let's say, and say subject to x less than or equal to 3. So x equal to 1 is a solution to the problem. It's not the optimum solution. So that way you have infinite solutions that exist. So even if I change that sentence to saying there cannot be multiple optimal solutions to a nonlinear problem, you can have situations where, but maybe it's very rare. The kind of problems that people look at would be very rare.
How do we connect ourselves to some renowned researchers in our area of work? Or can there be a provision where we are provided with an opportunity to discuss or understand from experienced or established scientists or professors to gain from their journey?
Again, it depends on who's asking this question. For example, is it a student who's studying undergrad asking this question? Or is it a person from industry who's asking this question? The answer can be slightly different for both. If it is an undergrad student or a graduate student or somebody who's asking this question, and I mean, there's one interesting answer. I mean, whoever you are, you can study, you can go to a university, you can study, and then you can establish connections with people who are around. That's a very standard answer. But if it is a young undergraduate student, the answer is even more specific, the same answer. If you are working in industry, there are opportunities for you to come The only thing you need to make sure is that you write to the correct person and you try to meet a correct person, try to find out what's. That's all. I mean, yeah, and you have to somehow take a chance in the sense whoever you are writing to, if that person is busy and this person is not able to give the time that you are seeking, then one has to accept it and then try to establish connection with another person. I think that's the kind of answer. Otherwise, I am unable to answer that. Occasionally, I do answer questions when some questions come to me by email, and I can't promise that I'm answering all the questions, but I certainly do answer. There are times when people ask some very specific things. There are times people ask some opinions, and I do give that to the best of my ability. I'm sure others will be doing something similar.
Please put some minimization problem in tabular form of simplex algorithm.
I'm not sure if I have done that here in this notes, but please look at my other 22 videos on operations research. I would have done the big M method there for minimization. So you can. I would have done the dual simplex algorithm again there. So that would tell you how to solve minimization problems. Those 22 videos are also available in NPTEL website as well as you can access them in YouTube. I think if you type fundamentals of operations research and type my name alongside, it will quickly take you to those videos and you can view them.
Sir, how is linear programming problem different than linear integer programming problem?
Okay. The difference is in a linear integer programming problem, your decision variables, at least one of them, has to take either an integer value or a binary value. In linear programming, you have a restriction that all the decision variables take continuous values. That's the first difference. In between, you have a class of problems like transportation and assignment, which we have done in this course, where even though they are integer programming in that sense, you don't have to because of the way the constraints are structured. So if you leave that part out, you can have this difference between the two, where in linear programming, all variables are greater than or equal to 0. In integer programming, at least one variable should be either binary or integer. Therefore, you can classify them as all integer when all the variables are integers. Mixed integer when you have some integer variables and some continuous variables. And you have examples of all these problems. For example, if you take a typical distribution problem which becomes a traveling salesman problem, then it is binary. It is all binary. If you are looking at some factory location kind of problem, there was a supply chain question starting of this discussion. So if you take a typical location problem, then you have variables for locating something and then you have variables for transporting something. So there you will have something like yj equal to 1 if a factory or a warehouse is located in a certain place. And then you will say xij is equal to something which is transported from a located factory or a warehouse to some other destination. So you can have the same problem where there are binary variables, there are continuous variables. So that becomes some kind of a mixed integer problem. You could also have problems where you have all integer, some integer variables and some continuous variables. So they become mixed integer linear program. The formulations, the way you formulate would be similar, but there are some little tricks or there are some little things that has to be observed when you do integer programming formulation. And I have also tried to address some of that in the videos of advanced OR, which are not part of this MOOC's course, but in the NPTEL. So there are another 40 odd videos for advanced OR. So there are topics in integer programming where I have tried to do some of these. But I think the very big difference is the way you solve both. Solving linear programming and solving integer programming are different. And I have tried to explain that in the videos, the other videos which exist. And you have very good books which tell you how to solve integer programming and different types of integer programming. If you are using a solver, it doesn't make any big difference. Only thing you have to do in the solver is to start defining the variable correctly, and the solver takes care of the solution.
Sir, an academic staff has posted this question. He wants to give his Bachelor of Engineering students some projects. So he's asking the current research area in OR and current trends in OR.
I have to assume that when you say an undergraduate student will be doing this project, so we have to assume that you are talking about some context in which to apply OR rather than looking at very deep into OR where at a very research level or even advanced level than that, you try to look at algorithms as well. So if you look at applications today, there are several application areas. Supply chain management is a very ripe application area. So you could think of distribution problems, traveling salesman problems, production planning problems, scheduling problems. So being an academic colleague, you should look at some research papers which tell you how research is actually moving. So if you see the general OR applications area, you can see applications almost everywhere. Today there is an increasing emphasis on OR in health, OR in education, and so on. Health is really picking up. So people look at models, how to model health systems, queuing models, other simulation models, even at times optimization models, how to allocate space or how to allocate surgery rooms to operations in a hospital. So all these exist. So there is a lot of opportunity. Just that you have to pick up the right area that interests you, and you can apply it. That's all we have at the moment. The other things which are there, everything has been addressed. Okay, so I think my students who are helping me with this, who have been reading out these questions, now tell me that we have kind of looked at all the questions. So if there are anything you can add to it, I'll be happy to answer. We'll give another 5 minutes to do that. Otherwise, if there are no more points to discuss, I think we can wind up. So it's about 10:40 in the clock in front of me. So let me wait for another 5 minutes for you to say something. Otherwise, we will wind up for the day. PG aware visible. Just muted for a minute.
What about the cyclic napkin problem for period of operation of maybe 1 week, that is week after week problem formulation? Then in general, what is the number of terms in objective function minimize Z?
See, if you take this napkins problem, let me try to answer this question. I think what I'm trying to understand is if the way the problem was done, we just talk about 8 days or 10 days. I think the person who has asked that question is trying to ask me what if, because this is going to happen every day. So how do I do that? I think that's the point. One easy thing to do is to, when you actually solve it as a linear programming problem, somewhere you have to define the time period. So it could be 8 days, it could be 10 days, it could be 1 month, and so on. So one has to do that. Because otherwise you will have to say that if I do for every week, And then you have to say that for every week, Monday, Tuesday, Thursday, whatever, Wednesday, all these demands are the same week after week. And then you can say that I can send something and I can still, for example, if you take 10 days and if you say that it takes 2 days to come from the laundry. So the formulation that we do will not have any napkin sent to the laundry on the 9th day because that can be used only for the 11th day. So if the question is about can I now send it on the 9th day and use it for the 11th day, then the thing is you should know the 11th day demand. And if you extend this logic, at some point you have to stop the planning horizon. So at the moment I don't see the problem getting into an infinite planning horizon because somewhere you have to stop, you have to do the planning horizon. The only thing you can do is you can extend the duration, you can do it for a month. Because I'm introducing it to a class or to an audience, I take 6 days, 8 days, 10 days. And I think in this course I've even shown you the solution using a spreadsheet. Whereas when you do that for a month, you will have a large number of variables. So you may be able to do it in a spreadsheet or you might want other solvers to solve it.
The academic who asked for the OR project for the bachelor students has said that my students are designing a plant layout for a small scale industry. What are the OR techniques we can use? It is a mechanical based firm for steel products.
If you're doing layout, as I mentioned, facilities, location, and layout is a separate area. There are some very good books. I remember a very old book, Facilities, Location, and Layout by Francis and White. I think there are further editions of that book. So you just try to look at that book, you will see the models that have been used. If you say layout, then you can have, there are also some things like layout packages which are there. So the simplest thing one can do is to minimize what is called the load distance in a layout. The normal quadratic assignment problem will talk about I want to allocate certain number of departments or certain number of things in certain places. So there is a W, which is a material movement, and there is a D, which is the distance. So you minimize the product of W into D, subject to constraints that each department goes to only one site and each site gets only one department. That's called the quadratic assignment problem. So if the problem that your students are trying to solve is amenable, you can do a quadratic assignment formulation. Normally, when you do it at an undergrad project and so on, you will have about 6 or 8 departments to be located. And if you are doing 8 departments, then you are talking of roughly 64 variables. I mean, Xij. No, you have more than 64 in this case. In this case, you will have something like 8 to the power 4 if you follow the quadratic assignment. Because you will be using a variable called Xijkl. And if each one goes from 1 to 8, you have 8 to the power 4, which is a very large number and you can't solve using a simple solver and so on. So the area shifts to now looking at heuristics to solve, looking at some other algorithms like evolutionary algorithms and meta-heuristic algorithms like things like genetic algorithms, simulated annealing, and those wide range of techniques that you can use. So all these can help do that project very well. We'll wait for a couple of more questions if there are any, and then we will. Okay.
There was a conceptual question by somebody. I would repeat that. Why do we divide the pivot row by the pivot element?
Okay. So why do we divide the pivot row by the pivot element? Let's go back to the algebraic form of the simplex. In the algebraic form of the simplex, I would have written, assuming you are solving a two constraint problem, there are two basic variables. And let's assume for a moment x3 and x4 are basic, and x1 and x2 are non-basic. So you will have an equation which will say x3 is equal to constant minus something into x1 minus something into x2. x4 will be constant minus something into x1 minus something into x2. Assuming you have all minus there. And then you will have z is equal to something into x1 plus something into x2. So the argument there is, I want to increase z, therefore the out of the non which are at 0, which is the one that gives me the highest rate of increase, which is given by the Cj minus Zj, and then put that variable into the solution. So that variable is currently at 0. So as you increase that variable, I would have shown you that the current basic variables will reduce because the coefficients are all minus there. So you keep increasing this variable till the first basic variable becomes 0. And that is called the limiting value. And that value is nothing but the value that the basic variable is taking currently divided by the coefficient, because that coefficient is going to represent the rate at which this is going to reduce and finally become 0. So when you start putting that in the simplex table, the only difference between the algebraic form and the tabular simplex is, if there is a constraint x1 plus x2 less than equal to 5, in tabular simplex, I would write x1 plus x2 plus x3 is equal to 5. In the algebraic form, I would write x1 as 5 minus x2 minus x3. So the plus and minus you have to see carefully. Therefore, the limiting value, the value which the entering variable can take, becomes the ratio of the right-hand side by the corresponding coefficient. So to find out the limiting value or the value that the entering variable takes, you do this. And then you call there as theta and minimum theta and so on. That's it.
I'm just hearing the response to the question on the new course, that multi-objective.
Okay, I'll repeat it, but I said that if you are going to ask me, am I going to offer that course? I think the answer is not at the moment, or not in the near future. That was the only answer. But the answer I gave was slightly different. I said, if you want to study multiple objective optimization as a separate course or a separate topic, it comes at a reasonably advanced level. So which means you should have done at least 1 or 2 courses in OR before you come to multi-objective optimization as a separate area of study. Therefore, I said and even if I assume, I may be wrong, I assume that if we do a separate multiple objective optimization course in OR, I think we may still have a large number, but right now I'm assuming that if I do a very general introductory course, it would benefit a larger number of students and audience, and therefore I am restricting myself. The answer that I also gave was, if you want some minimal exposure to that topic, I've given some videos in the advanced OR course where I have spoken a little bit about goal programming. That was the answer.
Can you tell me something about the question paper pattern and the standard level of questions in the final exam?
That's not an unexpected question in a webinar, but one has to expect that question. The only thing I will tell you is you are not going to have all MCQs, where I give 4 answers and you take them. You have a very small component of that. You will have some true or false, you will have some short questions which you compute and you type the answer and so on. So I think the exam would have you using the online calculator. no spreadsheets, nothing. There will be some problems where you work out, so slightly larger problems where you work out. It will be a combination of all of these. So you will still do a lot of problem solving. Because being an online exam, and I have not also used all the examination tools that are available, and I also don't have an idea how many people are going to take the exam. So asking you to formulate something is not easy in an online exam as I see it. For example, for some reason 1,000 people write the test and I give a formulation and I say that I will correct it. It's almost so difficult to correct 1 by 1,000 answer sheets. So therefore, this course would have you do a lot of problem solving and typing the answer so that the online correction is enabled.
Can you please share the reference of the books for plant layout? And will we get the book here? Can we buy?
I'm not sure. I mean, Francis and White was the book that I was mentioning. It's an old author and a good book. I think Facilities, Location and Layout by Francis and White. White is W-H-I-T-E and Francis is F-R-A-N-C-I-S. I am not sure whether Indian editions are available or whether you can buy the book. I think that is something you should explore with so many websites available for you to look at books. Please explore that. Otherwise, any book on operations management or supply chain management, production management. So those books will have one chapter on facilities, location and layout. You can read that also. But if you want a good solid presentation, then you should look at a book that is titled Facilities, Location and Layout.
Hello sir, I want to thank you for making me love OR. My question is, can engineering students do some small projects on techniques in OR for practical experience?
Don't get the question when you say techniques in OR. As an engineering student, you can only do a couple of things. Earlier, at least when we were younger and we were, or the days when we did not have so many open source solvers that were available, we actually took the trouble of writing code to solve simplex, writing code to solve assignment problem. And we used to do that. But today, I can't see an engineering student trying to do that because the student will quickly come back and tell, well, I can solve this problem up to this size. I have an open source solver. I'm not even bound by any this thing. I can do that. So, learning techniques today is either through courses like this where you work out problems and learn techniques. Typically, you don't learn problem solving techniques today by trying to write a code and then trying to test it on how well you have actually learned everything. But to that extent, this is my personal view. To that extent, that is the comment I have. And generally, when you are an engineering student in a college and you are doing a project that is related to OR, you will only find an application area where OR can be applied. And I have given you enough examples. I mean, you can do that in health, you can do that in education, you can do that in almost any area that you see. Distribution, those things come easily. So you could either even pick up some open problem and try. And so that's what you do when you are a young undergrad student trying to learn OR.
For theta in simplex table, we can't solve problem formulation if RHS of any constraint is negative. This numerator is negative, and also the denominator is also negative, which makes theta positive.
I have to answer this question because of a fundamental assumption that has been missed in the question. So let me reiterate this. Whenever you are solving a linear programming problem, you have to write the constraints in such a manner that when you begin linear programming, the constraints have non-negative values in the right-hand side. That's very important. Constraint has non-negative values on the right-hand side. So if you have a constraint x1 plus x2 greater than or equal to -1, then you will write minus x1 minus x2 is less than or equal to plus 1 when you do simplex. Or even when you are using a solver, at times solvers allow this negative right hand side, but it's good practice to write a constraint with the right hand side value either 0 or positive. That is a standard assumption, and in many ways it's a non-negotiable assumption when you are solving simplex. Therefore, the comment that says the numerator b is negative does not happen when you do simplex. Only the denominator can be 0 or negative. So when the denominator is 0 or negative, irrespective of what the numerator is, remember the numerator is 0 or positive. The denominator can be 0 or positive or negative. So irrespective of what the numerator is, if the denominator is 0 or negative, you don't calculate theta. So the only cases where you calculate theta are when both numerator and denominator are positive, when you have a positive theta value or positive value of the ratio, because it depends on what is theta. Sometimes theta is the minimum ratio. Sometimes we say find minimum theta. So depends on how you define that theta. So let's call the ratio and let's call theta as the minimum of those values. So you will calculate that value only when the right hand side is 0 or positive in the numerator and the denominator is strictly positive. So that what you calculate is either a 0 or a strictly positive value.
Will the final exam have any questions which have answers like with alphabets like M, N, or only we can enter numbers as input?
Can't say, could have something, but hopefully we'll find a way to take care of that. I mean, in the sense, this is I think the second or third or fourth time we are offering this course, and therefore we have some experience as to how to handle problems. So I won't say that, oh sure, don't bother about this M, N, A, B. I'm not going to say that. You could have a question where you have to type an answer which is A plus B.
In the simplex problem, why don't we use matrix multiplication for iteration instead of the row elementary transformation that you are using? I feel it would be simple for calculations.
Okay. Again, I have to answer this. I will. So what happens is when you approach this course or the way I was taught this course, when you start doing simplex, you do what is called the row operation way of trying to move from one iteration to another. There is also something called matrix method of simplex or something called revised simplex algorithm. I have addressed that I think I have addressed that partly in this course also. I have also addressed that in the other videos that are available, other videos of mine that are available in YouTube, in OR. Only when you use the tabular form, the way you do this row operations to get it is actually a Gauss-Jordan way of doing it. If you map it to an equivalent matrix method, it is Gauss-Jordan way of doing it. Particularly when you are doing it by hand, to make it easier and to save time, you do this row operation and get it. If you are actually solving a larger linear programming problem, let's say, even if you are solving a 20 variable, 10 constraint linear programming problem, and you are obviously not going to solve it by hand, and let's assume you are not using a solver and you have to write your own computer program to do that, then you will use matrix method. Therefore, matrix method is actually the thing that is happening. Tabular is only for us to understand what is happening when you do it in a notebook or when you do it on a board. So when you use the matrix method directly when you write a program, or indirectly when you use a solver that would use a matrix method. So matrix method is definitely used to solve. And then the onus shifts to how fast is the matrix method, which later shifts to what is the best way to invert a matrix or to solve equations. So what we used in tabular is the Gauss-Jordan way of solving. Are there methods which are slightly faster? Then one has to study this idea of complexity of the algorithm and speed of the algorithm and things like that. And it moved, and you can use different forms of matrix inversions. At some point, I would have explained the method that uses eta factorization of the basis in the other course and so on. So the actual answer is yes, matrix method has to be used and can be used. But it's not used in the table when you do it by hand, so that hand calculations are easier. We'll just keep one more minute if there is one more last question. It's more than an hour, about an hour since we started. We'll just give another minute, and if there are no questions, we'll wind up.
Any other method where research is going on in OR, if you want to develop a method?
Well, developing a method today is, I'm not saying it's impossible, but research is moving in certain ways. There are other methods that are available. If you actually go back to history, Simplex came somewhere around somewhere between 1945 and 1950 and so on. So it's almost nearly 70 years since Simplex came. The next major breakthrough to solve linear programming problems was what is called the Karmarkar's algorithm, which came in 1984. Normally, introductory textbooks and introductory courses do not do the Karmarkar's algorithm. Very advanced courses, graduate level courses alone do that. And that too, graduate level courses in OR departments do that. For multiple reasons, the way to understand one needs to understand a lot more mathematics than what is required to understand Simplex. And also to demonstrate even a 2x2 problem is not easy when you want to demonstrate it using a Karmarkar's algorithm. So those algorithms are more advanced and can work if you are solving a really large problem size. As long as you are in a reasonable problem space of about, let's say, 1,000 variables, 500 constraints, that kind of space, Simplex is still very good. So there's no reason to look at anything. Simplex has a very good behavior or performance to do this. And these, particularly Karmarkar's algorithm that came in the 80s, which itself is about 35 years old, solves problems with a very large number of constraints and variables. I think research is progressing, certainly progressing. People are working at coming up with faster and faster methods to solve these problems. But major breakthroughs, perhaps, we have to. So you see, there is a very major, significant breakthrough to solve LPs that come at some other time.
Any area, according to you, where we can develop a method for some new kind of problem faced by the industry?
Very general question. Very general question. Unless you know what is the industry, unless you know what is the problem, it's very difficult to do that. And I also don't know the background of the person who is asking the question. So normally what happens is problems that industry faces are being solved by themselves. The major companies have their own R&D establishments. And they have their own research groups that work, depending on the scope and depending on where they are. Service, manufacturing, domains. So different. At times they also come come to academic institutions and we interact with them to solve. So unless you know that here is a problem and here is a method, or there is no method right now to solve that problem, which is very, very rare. And only in such cases you start looking at methods. Otherwise, if you are looking at how to develop methods to solve problems, one has to understand what is called complexity of the algorithm that is being done. That's a separate field of study, and that depends on who is asking the question and what is the level of understanding the person has who has asked the question. But that's a separate field of study, and you have to study that. And it also doesn't happen instantly. It takes a lot of time to understand. First of all, to show that existing methods don't solve it, or existing methods don't solve it well, and then you look at new methods to solve. But methods keep coming. Methods keep coming in what is called the heuristic space, where you give good solutions, but you don't give optimum solutions all the time, because the problems are hard and difficult. Most real life problems are hard, and therefore getting optimum solution becomes difficult for large size. Then you look at rule-based solutions, heuristics. In that space, if you look at the last 20-25 years, several algorithms have come. That's why I spoke about these major breakthroughs and so on. So, I mean, easier asked than answered in some ways, unless you know, is there a problem which people are struggling to solve? And then can, first of all, an algorithm be developed? So even those are fields of study. So one has to understand that and then proceed.
What is degenerate solution in linear programming problem?
I think I'll explain degenerate solution in multiple places. So you have if you are doing simplex in particular, if you have an iteration where the basic variable is taking 0, then the solution is degenerate. So it can be degenerate at the optimum, it can be degenerate in the intermediate iteration. The reason for degeneracy happening in simplex is there is a tie for the leaving variable, so the other variable gets 0. At times when the formulation itself has a lot of zeros on the right hand side, the problem will become degenerate. The graphical representation of degeneracy is like equivalent of two corner points sitting one on top of the other. That's what degeneracy is. But degeneracy is generally seen only as a limitation of simplex. And simplex's inability, or times, because of this, simplex takes extra iterations. And therefore degeneracy is something that affects simplex. But it doesn't hurt in the sense it would eventually give the optimum solution when it exists. It might take a few more iterations, but it will. Yeah, I think we'll kind of wind up with this. We are about an hour and 5 minutes into it. So how many people? Any idea?
About 20.
About 20 people, I think, have joined. So thank you very much for joining, and it's been nice to interact. I hope I have answered at least a good number of the questions asked to the satisfaction of whoever asked that question. So as we wind up, I think let me thank the people who are here. Thank the two TAs, Swaminathan and Srivatsa, who have been helping me with this. Also thank Karthik, our NPTEL staff, who has enabled a whole lot of this. Karthik has been very good trying to record and edit many of the things that I have been doing. And Pradhyumna is also sitting here. So thank you very much, and let's hope you do well in the course, and this course helps you in whatever way it can to shape up a career in this field or in any other related field. So thank you very much, and have a good day.